is this taking so long to connect? Okay, let's get started. First, a couple of quick things. I graded all of the projects now. Now I have to start on the problem sets. For some reason, the last several computer assignments, some people are having trouble with Excel plots. And so what's happening is that you aren't getting a lot of significant figures. So equations for lines are showing up as y equals 0 times x plus 0. Even though you look at the graph and the trend line plotted, it's definitely not 0. Basically, Excel is truncating numbers and leaving out sig figs. And that makes these graphs very difficult or impossible to interpret. So if you see a graph like that, don't just submit it to me. I will take off points. Think about it this way. A lot of students get asked to bring major class projects or lab reports to job interviews. Would you bring a graph like that to a job interview, or would you stay up and figure out why on earth Excel isn't showing you more sig figs? So, I mean, I'm not failing anyone over that, but I am taking off points for a graph that I can't interpret. Any comments or questions on that? Okay, then what we're going to talk about today is we're going to talk about polarization of light and how that segues into quantum optics. So let me start here with polarization. I'll move these things over, change the view. All right, so when we talked about EM waves, we already talked about the fact that we have perpendicular E and B fields, and both of those are in turn perpendicular to the direction of travel. Now, the way I've written this wave out here, I said, okay, it's going to travel along the x-axis. The E field is polarized along the y-axis, and the B field is oriented along the z-axis. That's certainly not the only way we could do it. We could have the E field along the z-axis, the B field along the y-axis. But it's not like there's only two options. We could have the field oriented at any angle intermediate. We could have E along the y direction or the z direction or anywhere intermediate or down here or wherever. And these are all just linear polarizations. Linear meaning that the field always points in a line along the plus or minus y direction or plus or minus z direction, or plus or minus some intermediate direction. They have different orientations. They're all valid. And each of these is just a combination of the two above, all right? This field oriented along something intermediate between y and z is just a sum of this and this with some weighting coefficients. And that idea that an intermediate polarization is a sum of two other polarizations is worth hanging on to because it's going to come up again today. Now here's another weird way of doing it. We could write E as E naught y hat plus IZ times this complex exponential. And we would write B similarly. And this looks weird. For starters, this isn't a unit vector. The length of this vector is not 1. And we've just multiplied this by something complex. That shouldn't bother us too much because you got a complex number here, the sum of a cosine and a sine. And when we multiply everything through, we're going to get several terms. We'll just take the real parts. So let's do that. And if we multiply y hat plus IZ hat by this, well, y hat times the cosine is real. Y hat times I sine is imaginary, so we drop the I sine and keep that. IZ hat multiplied by I sine is minus Z hat sine, so we keep that. And we get something similar for B. And what we've got is we've got that the E field is a combination of the Y and Z directions, just like before, except that before, these coefficients were constant. Before, the E field was always along this axis, except when it was negative and into the page, but still along that linear direction. Now, the angle that the E field is making with the y-axis and that the B field is making with the z-axis depends on position and time. So now the E field is rotating. The E field is not just traveling and wiggling as it goes from one side to the other. It's now rotating, all right? The direction is changing, and not in the up and down way, but in a corkscrew manner. And we call this circular polarization because instead of tracing out a line like it would do here where it's just oscillating up and down, as it's swirling, it traces out a circle. And it's left circular polarization because the way I've written this, the E field, in time, the angle phi is becoming more negative. If I just fix the value of x and watch it go in time, phi becomes negative. So it's going to go into the page like this. And if I take the fingers on my left hand and curl them around the direction that the E field is moving in, my thumb points in the direction that the wave is traveling in. And we could also do something where we reverse some signs and we would get right circular polarization. And now I would take my right hand and I would curl my fingers in the direction that E is traveling. And my thumb would point in the direction of K. Any questions? So let's talk about how we would make polarized light. Well, one way, the most common way, it's cheap, it's not the most precise, but it's cheap, is absorption. You can find rod-like molecules that absorb energy if E is parallel to the direction of the molecules. And the way to think about that is that these molecules are basically wires. So it's not just about their geometry, it's also about their electronic properties. There are plenty of polymers that wouldn't polarize like this. But you find something that's rod-like and wire-like. And if I've got an electric field along the direction of a wire, well, current flows. And what do we know about wires carrying a lot of current? What happens if you feel those wires through the insulation? They're hot. So if they're hot, that means that energy has been transferred into the wire, okay? So energy has been taken out of the electric field that was being used to push current from your wall socket through the wire on your device. And it's been taken out of that electric field and turned into the kinetic energy of jiggling atoms in the lattice. Likewise here, we're driving a current, and if there's any resistance in those wires, and there is, then those wires will heat up. So this is one way to polarize. You get a sheet of this material. You could send in light that's some mix of polarizations. And anything that is vertical will be attenuated because all of that energy will be turned into heating up these wires. Anything that's horizontal or into the page, that'll pass straight through because this electric field, something that's oscillating in and out of the page like I'm doing right now with the cursor, that can't drive a current, that can't heat up the wires. Well, there's another way. We have seen in, you first derived it by hand, and now you're seeing it when you play with the thin film software. We have seen that reflectance of light is not necessarily equal for the two polarizations. There is a special angle where the TM light is 100% transmitted. The TE light is partly transmitted. So this stuff coming through here is a mix. This is pure TE. That happens when your angle of incidence is the Brewster angle. Now we can make the transmitted light almost purely TM by putting another layer and another layer and another layer and another layer. And so at each of those layers, some of the TE gets reflected. Some of it still gets transmitted, but all of the TM gets transmitted, and the fraction of TE light that will be transmitted after n layers will be a transmission coefficient raised to the n power. So you can attenuate that very rapidly, and that's what your assignment for next week is, to just play around in that code, adding more and more layers and seeing how many you have to add before we get that the transmitted light is 99.9% TM, and so the reflected light is 99.9% TE. You might say, shouldn't it be 100% TE? Well, there's always a little, because we haven't gotten these angles perfect, because we haven't done everything to an infinite number of decimal places, there's always a tiny amount of TM reflected in the simulation. And in real life, there would be a tiny amount of TM reflected because the interfaces aren't perfectly flat, which means that the light isn't always hitting at exactly the Brewster angle. There's going to be various imperfections that will cause you to sometimes be slightly off that angle, which will cause a little bit of TM light to be reflected. Now here's where it gets kind of fun. We can play with something called birefringence. The idea is that there are materials where the refractive index depends on the orientation of the E field. Basically, refraction happens because light is interacting with matter. And light can only interact with matter by shaking electrons, or by shaking protons. But the bottom line is by shaking charges. And the electrons are much easier to shake. So if you've got a crystal where the chemical bonds in one direction interact more strongly with an electric field than the chemical bonds in the other direction, then if I send in a wave polarized along here, well, I get a really strong interaction. I get a really large refractive index. I get a short wavelength. And if I send in light oscillating like this, I get a weaker interaction, a smaller index of refraction, and a longer wavelength. So I've got two waves that will be refracted differently. I've got two waves that will undergo different numbers of oscillations. And what if I took a wave that's an even mix of the two? All right, so it's oriented when it comes in at 45 degrees. Well, the y component will be multiplied by e to the I n2 k naught x. And the z component, going this way, will be all multiplied by e to the I n1 k naught x. And so the ratio is e to the I, difference in indices, k naught x. And that difference in indices is often 0.001 or smaller, which sounds trivial. Sounds like it's not something you could make use of. But you know, we're multiplying by k naught, which is huge. K naught is 2 pi over the wavelength, so it's 2 pi over a tiny number. So if I take 2 pi over a tiny number, multiply by a tiny number, I might get something intermediate, which I then multiply by x. And if I play my cards right, if I pick the right thickness for this, then I could get it so that after traveling a millimeter through a material, one of these polarizations has gone through an extra quarter cycle of oscillation, which means that the z component, that the ratio of the z component to the y component is I. And that is how we get the circular polarization shown here. Any questions?
So there's a pi over 2 phase shift between...
There can be if we pick the thickness right. If I made it thicker, then I can make that a pi phase shift, which means that the ratio would flip from being 1 to -1, and that would be a 90-degree rotation.
I see.
So people can make different phase plates like this. You'll hear about quarter wave plates and half wave plates. A quarter wave plate is not a quarter of a wavelength thick. A quarter wave plate is one where there's an extra quarter of a cycle of oscillation for one polarization relative to the other. And that will introduce this pi over 2 phase shift. It'll multiply one of them by I, and it will change the light from being linear polarized like this to being circularly polarized like that. Then there are half-wave plates, which people will use when they need to flip a polarization, when they need to take light that was originally polarized along this direction and turn it into something that's polarized 90 degrees away from that. So they'll make this ratio -1. Now, all of this requires that you know your initial polarization and that you orient everything just right, but this can be done. Other questions? Let's look at some pictures. Polarization gets used for a lot of things. By the way, you can tell these slides are old. I originally downloaded the pictures in the early 2000s, hence I found them on a GeoCities site. Light that's reflected is polarized, all right? So here's a picture of a forest without a polarizer. And remember that the surface of a leaf is often quite smooth. And because it's smooth, it produces glare. And the light is polarized, or the glare at least is polarized. So if we put a polarizing filter in front of the camera, we remove the glare, because if you think about it, the stuff reflected from the surface of the leaf, well, that hasn't gone into the leaf. It hasn't encountered any of the chlorophyll. The chlorophyll is absorbing red and blue and reflecting green. But the stuff reflected at the surface hasn't had a chance to go in there and interact with chlorophyll and have all of its non-green parts get absorbed. So the glare is going to be the color of sunlight, or disproportionately the color of sunlight. Whereas the stuff that goes in and bounces around in there interacting with the chlorophyll and comes out with a range of polarizations, that stuff will be green and it won't be as polarized. So if you use a polarizing filter, you can get rid of, not all, but a lot of the glare and keep the stuff that spent some time inside the leaves. Here's another example. Glare off of surfaces, all right? Here's a smooth surface. The reflectance will be polarized. So if you don't look at it with a polarizer, you see a lot of glare. If you look at it with a polarizer, we've just removed all of the TE light that was reflected off the front of the car and towards you. And this is why polarizing sunglasses are common, because a regular polarizer, if we just look at unpolarized light, it's an even mix of any two directions, whatever pair of directions you want to pick, all right? And the polarizing sunglasses absorb one of the polarizations and transmit the other. And if I'm just looking at light that's an even mix, I'm going to get 50% attenuation. 50% attenuation, if the sun is really bright, that's only going to do so much for you. And it's not going to change. If I just had plain absorbers that weren't polarizers, well, looking at this picture, I would see the car dimmer, but I would also see the person on the interior of the car looking dimmer. But if I've got something that strongly absorbs the TE light that was reflected and weakly absorbs the TM light coming from inside, then I get all of the TM light, or almost all of the TM light from inside. Of course, I lose all of the TE light from inside. That's a problem. But I also lose the TE light from here. And this light is disproportionately TE, whereas this light on the inside is only 50% TE. Questions? Here is a plot of reflectance versus angle of incidence for each polarization off of glass and water surfaces. This is, by the way, why you see in all of those plots in the thin film software that the reflectance versus angle for TE angles up. You get a minimum at 0, at least in some cases, depending on how you design the film. But for TM light, you get a maximum at 0. 0 angle. Now here's a crystal that is strongly birefringent, very different indices of refraction for one material, for one polarization versus the other? Well, the light coming off of this page is a mix of two polarizations. And because it's a mix of two polarizations, there's going to be two different kinds of refraction in here. Some of the light is going to get refracted by one amount, some of it's going to get refracted by a different amount. And so we see two images coming through this crystal. And you would use something with these kinds of properties to make a quarter wave plate or a half wave plate that would rotate the polarization. Any questions? Now, plastics are made of polymer molecules. They're not necessarily absorbing polymers, so they're not absorbing visible light. But polymers are just chain-like molecules, all right? They're very long chain molecules. And so even if they don't absorb light, they could still have a different refractive index for light that is parallel to the axis of the molecule, that's parallel to the chain versus perpendicular. And what that means is that light will undergo, the two polarizations of light will undergo different phase shifts. Now, if the polymers are coiled up, randomly oriented, you won't see any effect. But if the polymers are under some sort of pressure, and things that have been injection molded like this, oftentimes there are internal stresses in it, then there will be pressure, and that pressure orients the molecules and affects the optical properties. So now these become polarization rotators. They rotate, they introduce a phase shift into the polarization. And then when the light comes, so the light comes in, it's a mix of two polarizations. One of the two polarizations undergoes a phase shift relative to the other. And so you can get them to add up constructively or destructively depending on how many cycles it traveled through, or depending on the difference in the number of cycles. And because these differences in refractive index are tiny numbers, and that ratio of thickness to lambda is a big number multiplied by a tiny number can often be an intermediate number. It can wind up being a half a cycle. But because that wavelength in the denominator is different for different colors, for some colors you can get constructive interference, and for some you can get destructive. So to see effects like this, get some polarizing sunglasses, and then take a piece of injection molded plastic and look at it in the light of something with glare. So look at it with polarized light, and that just means, you know, holding an angle where it's going to catch some glare off of something, and you will see colors. So in grad school, I had to wear sunglasses for a while because I had an eye problem and bright light would hurt me. And I got some polarizing sunglasses that I could clip onto my prescription glasses. So a polarizing filter that would clip onto the front. On a grad student budget, prescription sunglasses weren't really an option. And so I'm wearing these polarizers, and you start to notice just how many surfaces really are producing polarized glare. Because you tilt your head slightly, you've just tilted the axis of the polarizer, and you see the reflection of the floor change. Because remember, I'm saying TE. I'm calling it TE, but TE is always relative to a certain set of axes. And normally you've got it set up so that the light coming off the floor is oriented disproportionately like this, all right? And so polarizing sunglasses have their absorption axis horizontal like this. If I tilt my head, well, suddenly this direction of the TE polarized light from the floor does not match up with the axis of the sunglasses, and so I can change the amount of glare that's transmitted through my polarizing sunglasses. So I learned a lot of optics going around for a few weeks wearing polarizing sunglasses in grad school. Any questions? It was really cool. I gotta say, being in grad school, studying optics while dealing with a very serious eye problem teaches you a whole lot of optics. I was having way too much fun with this. I mean, yes, on the one hand, I was worried and sometimes screaming in pain. But when I wasn't screaming in pain and I wasn't like, ow, ow, bright light, I'm like, whoa, this is pretty cool. Or, yeah, okay, I could see this with the sunglasses. Or, you know, I'd be thinking, why am I seeing a double image right now? Okay, well, I'm not on any, the meds wouldn't be doing that. Oh, it's because the bump on the cornea is generating a second image. It's acting like a secondary lens. So I actually had a lot of fun and learned a lot from having a serious eye disease while studying optics in grad school. I wouldn't recommend a serious eye disease. I wouldn't recommend any serious disease. But if you have to get a serious disease, get a curable eye disease, because you will learn a whole lot of optics from talking to your ophthalmologist. Again, don't get a disease, but if you must get one where you'll learn something.
Must have been an eye-opening experience.
Yeah, it was an eye-opening experience. I also like to say that the Norse god Odin sacrificed one of his eyes for wisdom. Well, I didn't sacrifice my whole eye, but I did sacrifice some function in my eye to get a PhD. So it doesn't quite rise to the level of godly wisdom, but it is very metaphorical. All right, on a more serious note, scattering of light by molecules can also polarize light, because if I have a non-polar molecule, this also works with polar molecules, but even a non-polar molecule, I've got light coming in. The light induces a dipole moment in the molecule. It causes the charges to oscillate along the direction of the electric field. And those oscillating charges are effectively little antennas. Now, an antenna produces polarized light. So let's say that the light coming in, first we'll consider the vertical. Well, if it's vertically polarized, I've got a dipole moment like this, and a vertical dipole doesn't scatter any light, all right? No light is scattered along the axis of the dipole, and you're thinking, but we got light right there. Yeah, that's coming from the horizontal. Meanwhile, the vertical dipole does scatter light that if it's perpendicular, if the direction of travel is perpendicular to the dipole axis, then the direction of the electric field is along the dipole axis. So this stuff, the light that's coming in vertical scatters vertical light this way. The light that's coming in horizontal, well, it produces a dipole moment like this. It can't send any light along that axis. But it can send light along this axis because this is perpendicular to that horizontal dipole moment that was created. And anything that comes out will be horizontally polarized. Now, of course, in this direction, well, the vertical dipole moment can send vertical light this way. The horizontal dipole moment can send horizontal light this way. So this light isn't polarized. And this light is partially polarized, and this light is partially polarized. But there are certain directions where the light is 100% polarized. So here are photos of the sky without a polarizing filter and with a polarizing filter. So with the polarizing filter, you get rid of the light that was scattered once. And you may be saying, well, there's still light that's coming out. Yeah, but that light that was that's coming from the sky got scattered at least twice in order to take that polarization and then flip it around. And light that gets scattered at least twice is disproportionately blue light. It's related to the fact that the sky is blue. If there were no sky, we would still see the sun. I mean, when the astronauts were on the moon, they had no problem seeing the sun. It's just that the light they saw coming from any other part of the sky, the only thing they could see coming from any other part of the sky would be starlight, because there wouldn't be any scattered sunlight coming from other parts of the sky. Well, on Earth, we have a thick atmosphere, so we see light coming from other parts of the sky. It's a scattered sunlight, but that light is disproportionately blue, because blue light can get scattered many times. So multiple scattering still comes from this part of the sky, but not single scattering. So the multiple scattering is unpolarized and blue. The single scattering is polarized and more yellowish, like sunlight. Questions?
So in the previous slide that you showed, so this, I just need like a little bit more explanation understanding this. So each of these pictures on the slide is like a moment where light gets scattered by a molecule. Is that correct? Or
Yeah, so we got a molecule here.
okay,
The sunlight is coming in,
got it.
and if the sunlight is vertically polarized, then we've got a vertical antenna. A vertical antenna sends polarized light this, vertically polarized light this way, and this way, and this way, and this way. And it sends something that's kind of intermediate in this direction. It sends nothing here.
Mm.
Some of the sunlight is horizontally polarized. A horizontal, and so it would make the electrons shake this way, like a horizontal antenna, which will send horizontal light this way and this way, but not this way. So there are certain directions where only one, and you could ask, what about the diagonal polarization? Well, again, we get a diagonal antenna here. And the diagonal antenna would send light polarized along that diagonal in every direction, except this one. It wouldn't send any light along that diagonal here, but it would send light that's at least partly along that diagonal in this direction, down here.
Right, right.
But not there. So what's happening is that along this direction, the light, if we were to draw a circle that's basically in this plane, within this plane, the polarization of light would always be along the edge of that circle. Out here, it's a mix. It's a skewed mix, more one than the other, but it's a mix. But along this direction, the polarization of the light will be along the edge of the circle.
Got it. Thank you.
And this circle is light that got scattered at 90 degrees with respect to the direction it came from. So in the morning, when the sun rises in the east, light coming from the eastern sky will be a mix of polarizations. And whatever light manages to get back scattered from the western sky will be a mix of polarizations. But light coming from the northern and southern skies or from directly up above will all be polarized because that light had to change direction by 90 degrees to get to you. And at noon, light coming from up in the sky, up above, is going to be unpolarized. But light coming from the horizon will be polarized because that light had to change direction by 90 degrees to get to you. Make sense?
Yeah, it does. Thank you.
All right. Final thing I'll say about polarization is that it's also the basis of liquid crystal displays. Basically, a liquid crystal is, again, a rod-like molecule. And what they do is they play with the transmission axis to gradually twist it. They can apply an electric field so that over here, all the rod-like molecules are oriented this way. And over here, they're all oriented this way. And in the middle, they rotate. And at each step, the transmission axis slightly changes. And the light follows the transmission axis. And so you can decide how much you want to twist that light to determine whether or not it gets through a polarizer. Those aren't used as much nowadays as they used to be, but they're still used, and that's the mechanism. All right, now we get, that's all classical optics. That could all be understood in terms of Maxwell's equations. All of this was known before 1900. There's something called spontaneous parametric down conversion. It's a nonlinear process. It's a process where you send in a photon with frequency omega 1, so energy h bar omega 1, and it splits into two photons. It's a rare process, so you need a very strong pulse of light to do it. And of course, it's more rare in some materials than others, so people tend to use something called BBO, beta barium borate. It's a crystalline material that just happens to do this relatively efficiently. In spontaneous parametric down conversion, basically one photon raises the system to an excited state. When it falls back to ground, it emits 2 photons. And by energy conservation, h bar omega 1 equals h bar omega 2 plus h bar omega 3. And this excited state is actually something called a virtual state, which is complicated, but suffice it to say that the downward transition involves 2 photons. Now, besides energy conservation, there's also momentum conservation. Photons have momentum. That momentum is h bar k. This is related to something you learned in 235 or 2540 about the de Broglie wavelength, where we learned that momentum is h over lambda, or lambda is h over p. All right. So if p is h over lambda, then we could take, we can multiply and divide by 2 pi, so we get h over 2 pi, that's, h bar, and we get 2 pi over lambda, that's k. So we have to conserve momentum. Now this is actually really hard to do. There's a reason why you need special crystalline materials for this. K is n omega over c. And the way I've drawn this diagram, K1 plus K2, sorry, K2 plus K3 that's a very poorly written 2, must be greater than or equal to K1. All right, and if we were to work this out in terms of angles, well, let's see here. K1 was in the x direction, so N1 omega 1 over C x hat, and then I left out the C's, oops. N2 omega 2 cosine theta 2 x hat plus N3 omega 3 cosine theta 3 x hat. And then in the y direction, we've got sines and we've got plus and minus. Getting the sine theta terms to cancel is not so hard. Positive and negative are naturally going to be, are by definition opposite. So getting these to be equal and opposite, not so hard. But here's the problem. Getting these to add up to N1 omega 1, that's actually difficult. Because omega 2 and omega 3 are both less than omega 1. And theta 2 and theta 3 are both less than 1. And if we look at a typical dispersion curve, refractive index versus wavelength, it looks like this. Now, short wavelength is high frequency. And we have a very high refractive index here. So we've got a large number on the left-hand side. And we've got a bunch of small numbers on the right-hand side. And yes, omega 2 plus omega 3 must equal omega 1, except that we multiplied omega 1 by a large number, N1. And we multiplied omega 2 and omega 3 by 2 smaller numbers, N2 and N3, and then furthermore multiplied by numbers less than 1. So this turns out to be a challenging condition to satisfy. And remember, we saw a lot of curves like this when we were playing around in ZMAX, looking through optics catalogs. There aren't a lot of exceptions to this rule. But what if the crystal was very birefringent and we set things up so that when the light comes in, the polarization is along the axis that gives you a small refractive index. And then we play around with things some more so that we're only, if we do that, then the photons that are emitted could be along the opposite axis, so we could have very large N of omega 2 and N of omega 3. And so that's why birefringence is important for these kinds of nonlinear optical processes, because it enables us to sort of make an exception. Even though if we were to just look at one polarization, for each polarization, the curve is going downward like this. But even though the curve is going downward, there are 2 different curves, one of them above the other. So if we play with our conditions just right, we can get it to produce 2 photons. going in different directions. And if we pick just the right angles and polarizations, the two polarizations are entangled and anti-correlated. They're entangled, meaning that as soon as we know one of them, we know the other. There's two possibilities. It could be that the photon going to the left had horizontal polarization. If that's the case, then the photon going to the right had vertical polarization. Or it could be that the photon going to the left was vertical and the one going to the right was horizontal. So they're anti-correlated in the sense that they're opposite, all right? Whatever one is, the other one must be the opposite of that. They're entangled in the sense that as soon as we know one, we know the other. And this is weird because I'm talking about this all in terms of horizontal and vertical. For starters, can't light just have any polarization? Well, sure, classical light, we could orient it any way we want. And in fact, quantum light we can orient as well. The photons come one at a time. So if I just send in a whole bunch of light to a polarizer, if I orient it like this at 45 degrees, I get half of it through. But any one photon coming through that, yeah, if I send in, 1 million photons, I get 500,000 out. But for each individual photon, it either goes through or it doesn't. Or if I set things up with polarizing beam splitters, it either gets transmitted or reflected. The photon can't be split in half. So I'm sending in a beam, I'm producing two photons going like this. And each individual photon is either reflected or transmitted. But we could set this up so that whenever a photon is reflected down here, the other one is transmitted. And whenever this one is transmitted, this one is reflected. Any questions on that? Well, here's where it gets weird. All right, as if quantum mechanics wasn't weird enough. You could say, all right, well, maybe we sent something in so that this photon was really, it would be horizontal in this case because it's TE. TE would be going in and out of the page, so TM would be going vertical. You could say, well, maybe we set up so this one was really really horizontal, and this one was really vertical. And then the next photon gets emitted, and just by chance, the next photon, the one going left, was really vertical, and the one going right was really horizontal. That's what we would like to think. We'd like to think that, all right, we set them up this way, and just by chance, we can only get one or the other. But here's the problem. Let's say we pivot the beam splitters. We switch things around so that TE relative to this surface, is no longer an electric field going in and out of the page, all right? Now it's an electric field going at some other angle. We rotate the other one the same way. Well, if this photon coming out here was really in and out of the page, that's what it really was. We're making this statement about what it really is. We're trying to hope for some sort of objective reality. And this one was really out of the page. Well, what is a photon that's horizontal going to do when it hits a 45-degree beam splitter? When it hits something whose selection axis is 45 degrees with respect to that. What happens in classical optics from what we just described? Before we got into the quantum stuff, what happened if we had, it could be an absorbing polarizer or a reflective polarizer. We've got something that selects a polarization that is going to reflect one polarization and transmit another, or absorb one polarization and transmit another. What happens when you send in light that's an even mixture of those two options? Half of it gets transmitted, half of it must get reflected. So if it's really vertical, but it hits something that's selecting along a different axis, well, then 50% of the time it should be transmitted, and 50% of the time it should be reflected. And the other one that's really horizontal, 50% of the time it should be transmitted, and 50% of the time it should be reflected, because it's hitting something that's 45 degrees. Okay. And indeed, when we rotate these and we do the experiment, 50% of the time this one reflects, 50% of the time this one transmits, 50% of the time this one reflects, 50% of the time it transmits. As long as I only look at one polarization, there's absolutely, sorry, as long as I only look at one of my detectors, or not one of my detectors, one of my pairs of photons, I only look at one side of the experiment, everything makes perfect sense. We should have 4 options, right? We should have transmission, reflection, transmission, reflection. Well, there are 4 options. There are 4 possible pairs. But here's the weird thing. 50% of the time, this one reflects and that one transmits. And 50% of the time, this one transmits and that one reflects. So no matter what we do, if I set this one up to select along, between into the page and vertical, and I set this one up to select between into the page and vertical, they're anti-correlated. If I set this one up on the left to select between 45 degrees this way and 45 degrees that way, so plus 45, minus 45, and I set this one up to show plus 45, minus 45, again, I get this. So I set up different axes, and the experiment still unfolds as if 50% of the time it was really, well, plus 45 degrees. And 50% of the time it was really minus 45 degrees. And whenever this one is quote unquote really 45, the other one is quote unquote really minus 45. And that's weird. No matter what axis we choose, as long as we do both of our measurements the same way, they're anti-correlated. Questions? If you're not arguing against this, then that means that you don't really understand what I just said. Because if you understood what I just said, you'd say, that is frickin' weird. It can't possibly be right. And if you are afraid to say that's frickin' weird, it can't possibly be right because you think it's going to make you sound ignorant of physics, Albert Einstein said, that is frickin' weird. It can't possibly be right, and argued against it and refused to accept it. And some people say, oh, that just proves that the great old man turned into a crackpot. No, that proves that the great old man asked a question that 30 years later resulted in something called the Bell theorem. Somebody took Einstein's question really seriously and determined that he was going to answer it one way or the other. And 45 years later resulted in something called the aspect experiment, named for a guy whose name was Alain Aspect. It's a French name. I'm sure it's not actually aspect. It's probably aspect or whatever. But the point is that the great old man, some people say he was a crackpot in his old age because he wasn't keeping up with the time. No, he asked a question. He said, this is freaking weird. It can't be right. And that motivated some of the most important physics in the second half of the 20th century. Again, as long as we choose our measurement axes the same on both sides, then these two measurements should be perfectly anti-correlated. Whenever one of them is 45, the other is minus 45. Whenever one of them is 0, the other one is 90, however we set it up. And of course, in reality, you could never get these two measurement axes perfectly aligned. They would never be exactly, the same, but they'd be within a few degrees or a fraction of a degree of each other, and you get almost perfect anti-correlation. Your correlation function is almost -1. Here's where it gets even weirder. You might say, all right, well, this photon comes in. It's forced to choose. It can either be transmitted or reflected. So it hits the mirror, makes a choice, says, all right, I guess I'm really going to be 27 degrees because that's how the experimenter decided to orient their mirror. And it sends a message to the other photon saying, hey, FYI, I decided to be 27 degrees, so you've got to be 90 minus 27 or 63 degrees. And the other photon says, oh, okay, I'm 63 degrees now. maybe there's some sort of weird communication. But you could put these two photons, you could put these two mirrors very, very far apart from each other. And if you put these two mirrors as a matter of fact, you could set things up so that these mirrors are, I mean, on Earth, we're talking still a fraction of a second, but people have done things with electronic timers where they know in advance, okay, a photon's going to be emitted at such and such time. It's going to arrive here however many microseconds later, because you set up a big experiment with a long baseline. So if it's going to take 10 microseconds to get there, at 9.8 microseconds, some electronics should randomly choose an orientation, rotate that polarizing beam splitter, and you may be thinking you can't rotate a mechanical object that fast. Well, what they actually do is they play around with something whose optical properties change when you apply an whose optical properties rotate when you apply an electric field. So if it's going to take 10 microseconds to get here, at 9.9 microseconds, choose an angle, and choose that angle with some electronics that can operate on sub-nanosecond time scales. That's fairly straightforward. Straightforward is a big word. It's something that can be done reliably these days. I'll say it that way. There's no time, and this one does the same thing, and they're independent of each other, and there's no time for the photon to communicate between here and here. So these two photons have to be acting independently of each other. And even when that happens, in whatever cases these two happen to choose the same axis, some fraction of the time these two measurements will be done along the same axis. In that fraction of the time, they're anti-correlated. There was no way for the photon hitting here to know that, hey, they were going to choose this angle, and then say to the other one, hey, if they also happen to choose to measure along that axis, make sure you anti-correlate with me. There's no way they could have shared that message, yet somehow they wind up anti-correlated.
So with this experiment,
yeah.
Did they use like a pulse laser system to do this, or?
Oh yeah. These are all pulsed lasers, and what they do is they send out weak pulses, and so you can either do weak pulses or you could do a very weak continuous wave beam. And no, let me think. Okay. You send in a pulse. Right. You're going to get a handful of photons coming out. If you send in an intense pulse, you only get a few photons coming out. You can make this, if you want to get a whole bunch of photons coming out, you need a really intense pulse. If you want to get hardly any photons coming out, use a weak pulse. So you set up the pulse so that on average you get one photon going each direction. Sometimes you'll get two photons. You'll get two clicks in the detectors. You could discard those measurements. So what you do is you set it up so that on average, every time you send in a pulse here, you get one photon going this way, one photon going that way. And if in that time interval you detect 0 photons here and 0 photons there, well, no harm done. If you detect 2 or more here, you just toss out that data. If you detect 2 or more here, you toss out that data. But if in a time window when you know that they should have been arriving, you get exactly one on this side, either down here or in there, and exactly one on this side, either in here or down there, then you use that data and calculate your correlation function.
Got it. Makes sense.
All right, so Bell looked at this and said, as long as we're thinking about experiments where we're measuring along the same axis, we've just got weirdness that we're shaking our fist at. So he imagined that we do measurements along different pairs of axes, and we switch between these pairs, and we don't necessarily require that any of these be the same on two sides. And he said, suppose that there's what we call a hidden variable. There's some variable that these two photons know about, and we don't know about it. It's something that doesn't show up in quantum mechanics, all right? There's some other variable beyond anything we've discussed in this class, in your quantum class, in a graduate level quantum class, something that's never showed up in a quantum textbook. There's some additional thing that we don't yet know in any quantum mechanics textbook at any level. And that additional thing that we don't know about tells the photons what they really are. And based on what they really are, they say, hey, if I happen to hit a polarizer that's oriented along that axis, I know exactly what to do. But if I hit a polarizer along some other axis, well, there's some rule that for a photon that's really in such and such state to decide what to do when it hits a polarizer at some weird angle. That rule could be something other than quantum mechanics. We don't know. It could be the most complicated rule in the world, but there's some rule. And whenever this photon hits something that's along an axis other than the one that it really wants, it will follow that rule. And this other photon will have to follow the same rule. And again, that rule will just depend on the variable and the axis. The thing is that this photon coming out here, it hits an axis that might be along direction A or A prime. And it doesn't know what's going on over here. It just follows its rule, which is some sort of continuous function giving a probability distribution for what to do if it hits axis A or A prime or whatever else. And this one follows its own rule, and it sees the same hidden variable, and it uses that variable and some function that we know nothing about to figure out what to do if it hits an axis oriented along B or B prime or whatever else. Now, you may be thinking that I'm leaving a lot vague and fuzzy. There's a whole lot that I'm just kind of waving my hands about and saying, hey, there's some rule we don't know. Here's the one thing that really matters for this experiment. We are assuming that this photon over here doesn't get any information on what this one's going to do. And that's going to really limit to what extent it can anti-correlate with this one. Because we know that if we set things up just right, these two are anti-correlated. If we measure along the same axis, they're anti-correlated with respect to each other. But now we've hidden all of that information. We've told this photon, you know your own state, you know what axis you're hitting, you can construct whatever function you like to figure out what percent of the time you should reflect, what percent of the time you should transmit. You say this one, again, construct your own rule to say what percent of the time you should reflect, what percent of the time you should transmit, but you don't know anything about that one. There are some inequalities that people have worked out involving the correlation functions of the correlation between the two variables. If we only consider four possible axes, A prime, B, and B prime. So C of A, B is, what if we happen to be using axis A on the left and we happen to be using axis B on the right? Then C of A, B prime is, what if we happen to be using A on the left, but now we're using B prime on the right? And then C of A prime, B prime, again, another pair of axes. So there are four possible combinations, and with each possible combination comes a correlation function. Using probability theory, someone worked out an inequality that they have to satisfy. And the key assumption there is that they never included any information on what the other photon is doing. And then they used quantum mechanics, and they calculated what these correlation functions should be using the predictions of quantum mechanics. And with quantum mechanics, we get violations of these inequalities. And deriving these inequalities is a rather dry exercise in integrals and various theorems from probability theory and basic calculus. But we get inequalities satisfied by these correlation functions if we have a hidden variable. If the photons are using common information available before the experiment, but neither one of them knows what's going on the other side. And then they did the experiment. And sure enough, in quantum mechanics, you can violate these inequalities, and the experimental data violates these inequalities. And the first experiments were done in the 70s. The more convincing aspect experiment was done in 1982. And since then, people have done lots more experiments to try to close loopholes. Like in the original aspect experiment, they didn't play around with the timing. They just chose some axes, did a bunch of measurements, then chose a different pair of axes, did a bunch of measurements. But you could always say, hey, maybe the photons kind of knew in advance. You know, none of these polarizers had rotated. So maybe there's some mysterious interaction going on where before leaving the crystal, the photons receive information on what's happening here. They know how this polarizer will be oriented. They know how that polarizer will be oriented, and they reach an agreement. And of course, photons talking to each other and reaching agreements is beyond any notion that even begins to make sense to us. But then again, so is quantum mechanics. Well, subsequent experiments have ruled that out. They've done these things with labs connected by fiber optic cables over very long distances. I forget what the current record is, but you know, first people did things with different buildings on the same campus, then different universities in the same town. I suspect that by now someone has done things over hundreds of kilometers of fiber optic cable. Still holds up. Another thing you could say is, hey, these detectors aren't perfectly efficient. You're always losing some data. There are times when a photon really did reflect or really did transmit, but because your detector was not 100% efficient, you lost that photon and you tossed out that data. And so one thing that people do is, of course, they say, all right, well, you know, we're only getting whatever percentage of the photons. What if all of the data that we're losing was actually satisfying this inequality? Could there be enough data lost so that if we included that data, we would suddenly satisfy this inequality instead of violate it? And in early experiments, well, you have some wiggle room. In later experiments, as the detectors got more efficient, they shut that down. And since then, people have searched for more loopholes, and every time they find a loophole, a clever experimentalist patches it. And so we're forced to conclude that somehow this photon over here knows what's going to happen or has happened over there. And it makes no sense to Einstein. And some people say, see, Einstein, there's this common thing where people like to portray young Einstein as a rebel misunderstood by the world rather than as a guy who actually got a pretty good job in the patent office, a job that many physics graduates would love to have. And they ignore the fact that within a few years of his major publications, he was getting very prestigious academic jobs and climbed the ranks quickly. And then they like to say, see, he turned into an old crackpot who couldn't accept the new science. No, he turned into a guy who looked at the new science and thought deeply about its implications and says, here's the one thing they haven't figured out. You really need to work on this. And yes, he was past his prime. He himself did not work out Bell's theorem. He himself did not propose the aspect experiment. But he looked at what was being done and said, yeah, there is something weird here. And when he said that, it inspired more than 80 years of work. People continue to do better and better tests of the Bell inequalities. Any questions?
Do you have any personal theories on what it could be that's correlating those two photons?
I have no idea. I think that we should take Bohmian mechanics pretty seriously. I think we should look at, now David Bohm did become a crackpot later in life, but there's a book called The Quantum Theory of Motion by Holland. I think it's Peter Holland. This book is completely orthodox quantum mechanics done in the Bohmian framework. And the beauty of it is that the Bohmian framework, the best and worst things about David Bohm's framework for quantum mechanics is that it makes 0 predictions that differ from orthodox quantum mechanics. That's a great thing because it means that it's not obviously crazy stuff that we can rule out on experiment. It's a bad thing because it doesn't offer anything new. But what it does offer is when you talk about quantum mechanics in the Bohmian framework, it's much easier to start framing hypotheses. It provides you with a way of talking where you can sort of make sense of ideas beyond conventional quantum mechanics. All right? It's like talking about, imagine that you're locked in, this turns into one of those philosophers' thought experiments. You know, people were raised in a cave and they never knew that there was a world outside the cave. Well, if you introduce the idea that the cave is not surrounded by infinite barriers, but by just rock of finite thickness. As soon as you introduce the idea that the rock around the cave has finite thickness, you still haven't really said anything about what's going on outside the cave, but at least you provided a language for talking about the idea that there's something beyond the cave. I think that Bohm provides some language for that. So I like this book, but it is a subtle read. And it ties into some of the most elegant ideas in classical mechanics, but it's sort of a natural starting point for studying things beyond orthodox quantum mechanics. Now, what just happened? Okay. So the aspect experiment was done in 1982. And it references the Einstein-Podolsky-Rosen Bohm thought experiment because in the 1930s, Einstein, Podolsky, and Rosen posed questions about these kinds of measurements, but they didn't go as far with it as Bell did. And then David Bohm elaborated on some of that in the 50s. And the aspect experiment involves, actually it was in reading about the aspect experiment that I first learned about polarizing beam splitters, which is why I thought it was worth talking about this when I had you do an assignment on the polarizing beam splitter. Nowadays, they don't do this by mechanically rotating a big block of glass. They do things with electro-optics, but the first experiment was done with these kinds of beam splitters. And what he said is that I showed you some inequalities before that all these correlation functions, when added up in a certain way, had to be less than 2. He came up with a result of 2.697 from his measurements and said that quantum mechanics would have predicted 2.7 for his experiment, and he got 2.697. So pretty good. Another thing that's worth mentioning, we can do more with these correlated photons than just test fundamental ideas of quantum mechanics. I told you last time about shot noise, about the fact that when you detect light, when you produce light in many cases, and certainly when you detect it, the number of photons that you get is given by something called a Poisson distribution. Well, some people 10 years ago did an experiment where they take pairs of photons, and one of the photons in the pair illuminates an object and forms an image on the camera. So of course, some of the photons are absorbed, some of them go to the camera. The other one just goes to a different region of the camera. It could be a separate camera if you wanted, but the details don't matter. And what they find is that you get a pretty noisy image up top because they're deliberately doing this in the low light regime. But now remember, everything, there's inevitably noise here. But they can reduce the noise by correlating the image of the object with the light that wasn't absorbed by anything. because you should have a simultaneous arrival of a photon up here and down here if the photon was transmitted. So any real transmission event up here, anything that isn't just noise, should be accompanied by a transmission event down here. And because not only are their polarizations entangled, but so are their momenta. They go in opposite directions. And so what happens is that if any real transmission event that isn't just noise is accompanied by a transmission event down here, then you can essentially use that to filter out noise and get much better imaging. And I feel like that's something that people haven't done enough with. I think the problem is then the kinds of physics I do, no one really wants to toss out half your photons. No one really wants to divert half your photons away. But I feel like there's still an untold story to be derived from this paper, that somebody needs to apply this work more than they have. And I don't know what else to say beyond that, but this is why nonlinear and quantum optics is worth learning. And I can recommend books on that, but I think that there's an untold story to be had from this. And it's a really interesting paper. And the nice thing about it, I think it might be subscription only, so I'll post it on Blackboard. A lot of papers in nature journals are accompanied by sort of a news and views section where the paper itself has lots of technical detail. But before the technical paper, they have a 2-page summary written for any reasonably well-educated scientist who might not be in that specific subfield. So I'm going to post this on Blackboard after class. But I feel like there's an untold story to be had here. Any questions? Then I want to switch from photons to neutrons for just a minute, and then we'll end unless people have questions about the upcoming assignment. Anything that you can do, any quantum weirdness with photons is really quantum weirdness with any kind of particle. And so a lot of important tests of quantum mechanics have been done by people studying neutrons, including Anton Zeilinger, who is most famous for his work on quantum optics as a fundamental test of quantum mechanics. But he's also done a lot of work with interference of neutrons. And what I really love is this experiment of his where he just sets up some new. Hey, how long was I out? It looks like I just got back into Zoom. How long was I out? Were you guys not hearing me for a while?
No, it just dropped and came back like super fast.
Okay. All right, good.
Dropped and came back like super fast.
Okay. Now I got to share the screen again. All right. So this experiment, they calculated what the diffraction pattern should be. They did the experiment. They got a diffraction pattern. Worked with a different setup. Calculated the diffraction pattern. Did the experiment. They match up nicely. These in and of themselves are nothing new. Diffraction patterns are nothing new. Here's what is new. They worked with very, very weak neutron beams. So weak, that they're getting one neutron every 2 seconds. Now, the time required to travel from the reactor to the detector was 0.1 seconds. And the time that the neutron spends diffusing around inside the reactor before going into the beamline. There's a reactor where the neutrons are emitted by radioactive elements, and then they bounce around a little bit, and then they exit the reactor, and they get collected and collimated and sent to the specimen. They spend roughly 0.1 seconds doing all that. But we only detect a neutron every 2 seconds because they're operating the reactor at very low intensity, which means that each neutron is only interfering, well, the neutrons aren't interfering with each other. It's not the particles that are interfering, it's the wave functions, this abstract wave function that determines the probability of the neutrons going somewhere. It's that wave function that's interfering, and it's only interfering with itself because each time a neutron is detected, the next neutron is still inside a nucleus. The next neutron has not even been emitted. And so this really kind of forces us to think about the wave function as a very real thing that exists independently of the particles. And that is also something that you can talk about in Bohmian language. Bohmian language provides a natural framework for talking about that. Questions? All right, so this is why I care about polarizing beam splitters. This is why I gave you an assignment on polarizing beam splitters. And the only things I'll say then for next week's assignment are, first of all, if Excel is giving you weird plots, please work on the significant figures in there. And also, remember that the layer thicknesses are lambda over 4n cosine theta, and you're going to have to use Brewster's angle to figure out what theta should be in each layer. Have a good day.